Thinking about our upcoming test here, we have 6 total targets that we're going to be working on. So I'm just going to go through those kind of in the order that they show up on the front of your toolkit and give you some examples of what you could expect. So the first target that I have is rewriting expressions in different formats. So you're going to see this across 3 different ways. First way would be like our ABE to BAE sort of thing, or our logarithm to exponential, depending on how your teacher talked about it. Factoring and completing square are all different things that would show up as part of this rewriting target. So the way that I explain logarithms and exponentials in my classes is to use what I call ABE to BAE, which is just a format for rewriting the two. Now, I try and use really logical letter choices here. So I use ABE to BAE because the letters stand for 3 different things. So A stands for answer. So the answer is on one side of the equal sign here. Answer is in there over there. B stands for base. And E stands for exponent. So I get these 3 letters from the exponential setup. So A, answer, B, base, E, exponent. So then when you rewrite, this is where those letters would end up. So the B ends up being the little number below the logarithm. The A ends up being the number inside the logarithm, and the E ends up being the piece on the other side of the equal sign, but they still represent the same things. So for example, in this particular case, my A would be Y, my base is the 3, and my exponent is the X. So if I want to rewrite that as a logarithm, it would become log, our base is 3, so 3, our answer is Y, equals X. And this is rewritten as a logarithm. That's an L. You can also do the same thing in the other direction. So starting off with a BAE setup and turning it into an ABE setup. So looking at this, you might notice that my equal sign is on the other side. It's no big deal. Sometimes we will do that to you on purpose if it makes you feel more comfortable. You can move the equal sign to the other side so it would look like this. And now I can rewrite using this BAE setup. So B is down here, A and E, so I can rewrite it as an exponential. So my answer is X, my base is 6, and my exponent is the Y. So these have been rewritten using ABE to BAE formatting. Now, rewriting is just the idea of changing how an equation looks. It's not necessarily solving, it's not necessarily getting to a specific place, it's just like rewriting it in a different way. So another way that we go about doing that is by factoring. So in terms of factoring, we usually use like a box and diamond sort of setup, so that's how I'm going to format this. So I need 2 numbers that are going to multiply to make 90. X squared, in case you're wondering, that is 18 times 5. So always this first number and last number multiplied together. And then it needs to add to 19. Some of us are going to be really, really fast to find those numbers, some of us not so much. So I'm going to pretend I'm not so much today. If that's the case, what you would do is just make a list of the factors of the number you're multiplying to make. So 1 times 90 multiplies to make 90. 2 times 45. 3 times 30. And how I would do this in my calculator is I would just do 90 divided by 1, get out an answer and say, oh, 1 times 90. 90 divided by 2. Oh, it works. Get out an answer, write them down. 90 divided by 3. Oh, it works. Get out an answer. And then I would test 90 divided by 4 and happen to notice that it doesn't work, so I'm not going to add that to my list. 90 divided by 5. And see that that works. 90 divided by 6. And I'm just going to keep going until I get to a point where I start seeing repeating numbers. So 7 doesn't work. 8 does not work. 9 would work. And then if I kept going, I would get 10 and then 9. So I see a repeat, so I don't need to have that one on here. And then off of this list, these are the only pairs that I can consider. I'm looking for the pair that adds to make this bottom number of 19x. So 1 plus 90 obviously isn't 19, so I would go through my list until I find the pair that works. In this case, it is 9 times 10. So what that tells me is those are going to be the 2 boxes of x's in my box and diamond setup. Now the 5x squared goes in here as normal, and the 18 goes in here as normal. What I do from there is I cover up one side of the box and I say, okay, what do these 2 pieces have in common? What are they both divisible by? And whatever they're both divisible by is going to be what goes up here. So 5 and 10 are both divisible by 5. They both have an x, so 5x is going to be what goes up there. Once I have that in place, I say, okay, what times 5x gives me 5x squared? And whatever I say is going to be what goes over here, which in this case is x. And then 5x times what gives me 10x? Well, that'd have to be 2, so that's going to be what goes here. And now that I have those three pieces in place, I remove my hand and I say, okay, what would I have to put here to make this all work out? So x times something needs to make 9x. That something has to be 9. And then I can use this as a check. Does 2 times 9 actually make 18? And it does. So I can rewrite our green expression here, 5x squared plus 19x plus 18, as 5x plus 9x plus 2. Again, since we said we're just rewriting, we're not actually solving, that's all I was looking for in this case. Could you have gone through and solved and figure out what x would have to be? Sure, but that's not what the problem here is necessarily asking. Moving on to completing the square. Whenever we're dealing with completing the square, the first thing you're always going to want to look for is there a number out front of the x squared? If there is, you want to factor that out. Even if it's going to leave you with a decimal at some point, you do not want that number in there. So I'm going to take that out kind of like reverse distributing. So 3 times x squared makes 3x squared. And then I have to say 3 times something is going to make 18x. In this case, negative 6x. 3 times something needs to make positive 3, so plus 1. And then for the moment, we're just going to kind of pretend that that 3 doesn't exist. And we're just going to look at this stuff for now. Now, completing the square is very different than factoring. We use a very similar looking setup, but it's very different. The difference is that a square has to have equal sides. So down here we had 5x and 9, 2x and 2. These are not equal things. So this is not a square. This is really a rectangle. Up here, when I say square, what that means is these two sides, whatever I put on either side has to be the same on both sides. So when we go into completing the square, the big difference in how we deal with it is I'm not going to care about that plus 1. So not only are we not paying attention to the 3 that's out front right now, we're kind of ignoring this 1 for the moment. And I'm saying I need to organize these two pieces into our square so that things are equal on both sides. Now, the x squared still goes in the upper left like always. But in completing the square, since we need that 6x to break up evenly, we say this is going to have to be negative 3x and negative 3x. Because that's going to lead us to having a square. Since these are the same number, that means the sides will have to be the same. I'm ignoring this bottom box for a moment. So now that I've got most of my stuff in place, I can set up the sides of the box. And like I said, they have to be the same. Since these are now the same, they cause me to get a box down here of 9. And the real difference in completing the square is we say, okay, what do I have to do to get back there? And really what I have to do is take away 8. So we're going to rewrite our original quadratic equation using this idea. So the 3 out front is still there. We're ignoring it, but it's still there. X minus 3 squared is our box. But what we said is, oh, I didn't actually need 9. I only needed 1. So we have to take away 8 from our square. The last step in completing the square is just distributing this. Now, you're not going to distribute into that second set of parentheses. You're only going to do it in front of this x minus 3 squared and then to that piece. So the final version of this rewritten expression will look like this. And if you were to graph this or this, you would get the exact same parabola. And again, I didn't actually ask you to solve. I only asked you to rewrite. So rewriting would be just like this, and you're done. You wouldn't have to actually go through and solve. Moving on to our next target, it's systems. Now, you could do systems in 2 different ways. Now, some of us have talked about 3-variable systems. That's not on this test. Keep in mind that's Chapter 6 stuff. That is not Chapter 5 stuff. So I have 2 different problems. We're going to do substitution and elimination. Keep in mind, substitution is the idea of plugging one system into another. So I see that this equation is set up so that y is by itself. So what that tells me is I'm going to take this and put it in the place of the y up here. So I get x squared minus, because x squared minus, negative 2x plus 2 equals 1. Back in our Algebra 1 days, we talked about how you distribute this negative sign. So x squared plus 2x minus 2 equals 1. Hopefully this starts to look really familiar and you go, oh, hey, that's just a quadratic equation. I definitely know what to do here. I need to get I need to get the one side to be completely 0 and then I need to solve this like I would any other quadratic. In this particular case, it's set up really well to factor, and just in the interest of time, I'm not going to go through and show the box, but I'm doing what we did up here for using the box and diamond. But it would be x plus 3 times x minus 1 equals 0. And if you were to multiply that all out, we would get here. However, in this case, since it's a system, I am actually asking you to solve, so you would need to go through and find your x's, which in this case would be -3 and +1. Keep in mind, those are just whatever makes each parenthesis work out to 0 is our two x values. Now that I found x, I'm not actually done. I have to take those back up here and plug them into one of my two equations and solve for y. In my opinion, the bottom one looks a little bit easier, so I'm going to plug these into this bottom equation. So I would say y equals -2 times -3 plus 2. So y equals 6 plus 2, or y equals 8. And then if I plug in the 1, exact same setup, I get 0. So my solutions should be written as a pair of coordinate points. And since I plugged in -3 and got out 8, that's my first coordinate pair. And when I plugged in 1, I got out 0. That's my second coordinate pair. So this would be what I would be looking for in that case. This equation is set up for elimination. Now keep in mind the difference is that in substitution, we have one letter that's solved. It's all by itself. In the other one, we usually don't have that format. What we're looking for is the numbers in front of the x's or the numbers in front of the y are the same but opposite. So like 10 and -10 or 4 and -4. I don't have that right here, but what I do have is a situation where I could make this equation so that the number in front of the y is a +4, so that the 4 down here would eliminate with the -4 up here. How I would do that is I would multiply this entire bottom equation by 2. Now you'll notice that in my work, a lot of times people like to try and skip steps and not rewrite things. I refuse only because I know that I'm going to make a mistake if I don't actually go through and rewrite everything as I do it. So I show my work of, hey, I'm going to do this times 2, because that helps me keep track of the math that I'm doing and helps me catch mistakes later if I make them. So 5 times 2 is 10, 2 times 2 is 4, 18 times 2 is 36. Now I'm in a situation where I have a -4y and a +4y. So if I were to add these two equations together, those y's are going to make 0 y's. And I get 13x equals 26. From here, I can solve for x by dividing by 13 on both sides, and I get x is 2. Now that I've got my x value, I'm going to take it back up into one of my original equations and solve for y. It does not matter which one, whichever one looks easier to you. I tend to avoid negative numbers if I can, so I'm going to use the bottom one. So I'm plugging in 2 for x, and I'm going to solve for y. And I get y to be 4. So that means my coordinate solution is 2, 4. So that would be systems that you could expect to see. Moving on to our next target would be expressions in equivalent forms, which in this case is going to refer to those big scary fraction looking things that we've been talking about over the past several chapters. Again, in the interest of time, I'm not going to necessarily show every single step, but a lot of what I'm going to have to do here is this idea of factoring that we did on our first page. So if you see me going from something that looks like this to something that looks like this, that is what I'm doing, is I'm using box and diamond to factor. I'm just not going to show it all of the boxes just to save us some time and energy here. So whenever we're looking at any sort of multiplication problem, the first thing that you're going to do is factor all of the pieces. So if I do that here, I get x plus 2 times x plus 5 over x plus 6 times x plus 2 times x minus 3, x plus 2, x plus 5, x minus 3. Okay, so I've gone through and done all of my factoring. Again, I use the box and diamond on each of those. The nice part about multiplying fractions is that there's really very little you have to do. Essentially, what you're going to do from this step is when I'm multiplying, it just becomes one big giant fraction. And then what I'm looking for is any big giant ones. So the idea of like something over itself that is the same. And this could go cross fraction because like I said, it's one giant fraction now. So I see an x plus 2 in the numerator and an x plus 2 in the denominator. Those make 1. I see an x minus 3 and an x minus 3. So those make 1. I see an x plus 5 and an x plus 5, so those make 1. And anything that is left is going to be our reduced fraction, in this case, x plus 2 over x plus 6. I would expect you to write out any excluded values, which comes from these missing pieces. I would write x cannot equal, and then whatever makes each of them work out to 0. So in this case, negative 2 plus 2 is 0, so x cannot equal negative 2. X can equal negative 5 from the second one, and x cannot equal positive 3 from the third. Technically, you don't have to write it for the one that remains because that's going to be an asymptote, not necessarily in a whole. But if you wanted to, I would not give you a hard time if you wrote x can't be negative 6 as well. The only main difference between multiplication and division is the very first step. What you're going to do before you do anything else is if you see multiplication or division, you have to rewrite your expression as multiplication. So that would mean our first fraction is going to stay exactly as it is. But our second fraction is going to flip upside down, and then it's going to become multiplication. Now, we talked in class about why this works the way that it does. Essentially, it's because you're multiplying by the reciprocal in order to make things cancel out. If you're curious about more of that, let me know and we can chat later. Now, from here, we treat it exactly like we did the multiplication problem. So the first thing we're going to do is go through and factor all of our pieces. Something that I like to do, especially in these bigger divide type problems, is I'm going to look and see, is there a number I can pull out of all three pieces? In other words, a number that all three of them are divisible by. In this case, I see a 2. So 2, and if I were to divide all of these by 2, I get x squared minus 5x plus 4, and that's a lot easier for me to factor in my head. So x minus 4, x minus 1. This would be x plus 8, x minus 2, x plus 8, x plus 2. This one is also divisible by 2, so I'd pull a 2 out of both of those pieces, and then x plus 2, x minus 2. In general, just as a little hint, if you ever see a piece like this where there's only 2 pieces to it, and one of them has an x squared and one of them doesn't have an x at all, it factors. Check. Usually the way that these ones are going to work is in your box and diamond. Let's just pretend for a moment you didn't factor out that 2 like I did. What this is saying is negative 16x squared and 0x. So I need 2 numbers that multiply to 16 and add to 0. In this case, it would have been 4 and negative 4. If you had gone through and divided out the 2, you would have ended up with x squared minus 4. So negative 4x squared and 0x. And again, it would have been 2 and negative 2, which is how I got here. So if you ever see one like this where it's x squared and then just a number with no x, it factors. Almost guaranteed. Check. Now that we've gone through and done all of our factoring, like we said, it is one ginormous fraction. And then I'm looking for giant ones, things that are the same on top and bottom. So I see an x plus 8 and an x plus 8. Can get rid of those. I see an x plus 2 and an x plus 2. I see a 2 and a 2. And then what's left is going to be my answer. You will notice that sometimes I'm going to intentionally set up situations where it looks like it should simplify, but it doesn't, especially if you forgot to do your flipping and then turning it into multiplying. And again, I would be looking for excluded values, so x cannot be negative 8, x cannot be negative 2. There is no excluded value for 2 over 2. You wouldn't have to worry about that one. If you chose to write this as x minus 2 squared in the denominator, that's also fine. So multiplying and dividing are very, very similar. The only difference is this one step at the beginning where you flip your second fraction over and turn it into multiplying. Adding and subtracting, however, are a little bit different. So adding and subtracting, what you're going to need is common denominators. Just like if I wanted to do 1/3 plus 1/2, I need common denominators there. So the way that we did that back in this step is we would have done multiplying by 2 over 2, multiplying by 3 over 3. So we end up with 2 over 6 plus 3 over 6, and then we would have added our numerators. Same idea here. The only real difference is that our denominators don't quite look like that. Again, the first step we're going to want to do is factoring. So I'm going to factor this denominator. So I get 5x over x minus 2, because there's nothing to factor there, plus 3x minus 1, because there's nothing to factor there, over x minus 3 times x minus 2. And what I notice is that both of these fractions have an x minus 2, but this fraction has the x minus 3 and this one does not. So that's going to be what I need to multiply this first fraction by, because then I'll end up with common denominators. So when I do that, I will actually do the multiplying in the numerator. So that would give me 5x squared minus 15x over, but I'm not going to do any of the multiplying in the denominator. I'm just going to leave that alone. From here, we're going to combine our like terms. So we're going to add our two numerators together. So I get 5x squared minus 12x, because negative 15x plus 3x would be negative 12, minus 1. And then over our same denominator, again, I'm not going to go through and multiply that out, because in the end, what we would be looking for is, does this numerator factor to simplify? So are there two numbers that multiply to make 5x squared and add to make 12x? Conveniently, or negative 12x. Conveniently, this does not factor. This isn't an option. So this would be our final answer. Again, I would be looking for those excluded values. So x can't be 3, x can't be 2. Moving on downward, the next thing on our targets is solving and checking for extraneous solutions. So solving is going to be any type of equation that I could expect you to solve. Things like absolute value, radicals, quadratics. It could even be linear. Just any type of equation that I would expect that you are able to solve. Then you're going to have to check and see, do those solutions actually work? That's what we mean by checking for extraneous. So I just gave you 3 different examples of things that I would expect that you should be able to solve. Now, in absolute value equations, what we said is that the absolute value piece needs to stay together until the very end, so I've got to get rid of everything outside the absolute value first. So I'm going to add the 1. So I get 2 absolute value of x plus 3 equals 2. Divide by 2 on both sides. X plus 3 equals 1. Now that I'm here and the absolute value is by itself, what I'm going to do is create 2 separate equations, because technically what this is saying is x plus 3 could be 1, but x plus 3 could equal negative 1, because the absolute value of negative 1 is still 1. So I'm going to set it up as x plus 3 could be 1, or x plus 3 could be negative 1, and it would still make this equation work. From here, I can solve for my 2 solutions. So I'm going to subtract 3 on both sides, and I get x equals negative 2, or x equals negative 4. Those are my 2 solutions. Now, to check if they are extraneous, what you're going to do is plug them in one at a time back to your original equation and see, does it actually work when I plug it in? So if I plug in negative 2 up here, I get 2 times the absolute value of negative 2 plus 2, or plus 3, sorry, minus 1 equals 1. So in a calculator, if you wanted to, or just in your head, negative 2 plus 3 is 1. Absolute value of 1 is 1. So I have 2 times 1, because negative 2 plus 3 is 1. Absolute value of 1 is 1. 2 times 1 is 2, minus 1 is 1, so I do get 1 equals 1, which is a true statement. Then I'm going to check on the other side. So 2 times absolute value of negative 4 plus 3, minus 1 equals 1. Negative 4 plus 3 is negative 1. The absolute value of negative 1, like we said, is 1. So 2 times 1 is 2, minus 1 is 1. So 1 equals 1. Neither of these are extraneous. So then what I would be looking for is you just leave it like this. Done. Moving on to the radical. This is where a lot of you really, really struggle. The first thing you're going to want to do with any type of radical function is you want the radical itself to be alone. So nothing after it, nothing before it. So I don't want to see a 2 out here. I don't want to see like a minus 5 at the end. None of that. If there is anything, get it to the other side first. In this case, it is all by itself. So what I'm going to do is get rid of the radical by squaring it. But if I do that on one side, I have to do it on the other. Most of you, if you're going to make a mistake with these, it's going to be in this immediate next step. So when I square and square root something at the same time, those just cancel out. So I get 3x plus 16 over here. On this side, this is where a lot of you panic. You go x squared or x plus 2 squared. Oh, I can just distribute that squared. But no, you cannot. I'm actually asking you to do like the box, saying x plus 2 times x plus 2. And if you were to do the box, what you would get is x squared and 4. Yes, just like if you were to distribute. But you're forgetting about these 2 side boxes if you do that, which is 2x and 2x, meaning I should also have a 4x over here. Now that I'm at this step, I'm going to get everything to one side, just like we did every other time we've done any factoring or quadratic problems. So I'm going to subtract the 3x, subtract the 16, both to the other side. and I get x squared plus x minus 12. From here, this is now set up for factoring, so I go use box and diamond, and I get x plus 4, x minus 3. Now that I've gone through and done that, I need to use my solving, which is what makes each of these work out to 0. X could be negative 4, x could be positive 3. So those are my two solutions. And now I have to plug them in and check and see, do they actually work the way I think they will? So I'm going to plug each of them in to my to my two sides of the equation and see if they work. So the square root of 3 times negative 4 plus 16, is that the same as negative 4 plus 2? 3 times negative 4 is negative 12, plus 16 is 4. So I get the square root of 4, and then over here I get negative 2. The square root of 4 is 2, and that does not equal negative 2. So what this is telling me is that negative 4 is extraneous. I'm not done though, because technically both of these solutions could be extraneous, so I do have to check and see if 3 is going to work as well. So 3 times 3 plus 16, is that the same thing as 3 plus 2? So 3 times 3 would be 9, plus 16 is 25. So I'm taking the square root of 25. Over here, that get 5. Square root of 25 is 5, so 5 does equal 5. That means this other solution is totally fine. So all I would be looking for is for you to label, hey, negative 4 is extraneous, but 3 is not. So if you wrote just like this on your solution page, totally fine. Finally, quadratics. All I'm looking for is for you to solve using whatever method you choose. This one is set up really easily for factoring, so I'm just going to use factoring. So in order to factor, I need to move that 24 to the other side, get 0, and then set up a box and diamond. Again, if I'm able to, I like to factor out any numbers that are out front as best I can. In this case, I see that all of the pieces are divisible by 2, but not 6. So just to make my numbers a little bit smaller, I am going to go through and divide everything by 2. This is not at all necessary, just to be clear. And then I'm going to ignore that 2 and see if I can do the box and diamond on these two pieces. So two numbers that multiply to negative 36 and add to negative 5 would be negative 9 and positive 4. So then setting up the box, 3x squared, negative 12x, negative 9, or not negative 12x, negative 12, negative 9x, and 4x. And again, just using the box and diamond like we did on the very beginning of these problems. So I get 3x plus 4, x minus 3 equals 0. So my two solutions in this case are x is negative 4 over 3, and x is 3. If you're curious how I got here right away, essentially what I'm doing in my head is I'm creating a little mini problem where I say 3x plus 4 has to equal 0, and I'm solving for x. Now that I got my two solutions, I have to check and make sure they actually do work when I plug them back in. So if I plug into my equation, so negative 4 over 3 squared would be 6 times 16 over 9. This would be 40 over 3. Doing the math here. And if you were to type this into a calculator, you would get 72 over 3, which is 24. So negative 4 over 3 does work as a solution. Then I'm going to plug in 3 and do the same thing. So 6 times 3 squared minus 10 times 3 equals 24. So I get 3 squared is 9 times 6 is 54 minus 30. Is that the same as 24? Which it is. So that means both of those solutions work, and that is totally fine for us to get. Now, when I'm asking you to check for extraneous, I do need you to show this. Even though they do work out, I need you to show this in order to prove this target, is that you understand that you are checking to make sure those solutions work. Moving on to our last couple of targets. create, graph, and describe an inverse equation. So first things first, I'm going to give you some equations and I'm going to ask you to determine if they are inverses. So for example, here are two equations and I might say, are these inverses? Lots of different ways you could go about checking this to be sure. The way that I generally choose to do this is I take my original equation and I'm just going to switch x and y. And then solve for y. So I took this original equation, I changed this out for y, and I said, okay, switch x and y. So x equals 2 times y minus 3 cubed minus 6. That's how I got here. Then I'm going to solve for x, or solve for y. So I'm going to get the y by itself. So I have to add the 6 to the other side, and then divide by 2. Now I have to get rid of that cubed, so I'm going to cube root both sides. And then I have to add the 3. And at first you might think, oh yeah, these are totally the same equation, but I'm being a little bit picky here because this cube root is only showing up over the top of the fraction, not the whole fraction. So these are not the same, which would mean that these are not inverses because this is what should be the correct inverse of our original equation. Okay. I might ask you to just find the inverse of an equation. So I might give you something that looks like one of these two and ask you to find it. Again, the easiest way in my opinion to go about doing that is to take x and y and switch them. So this would become x equals 3y plus 4 over 2 and then go through and solve for y. So I would multiply by 2 on both sides, subtract the 4, and then divide by 3. So this would be my inverse. Then I would do the same thing here. So switch x and y, and then start solving for y. So add the 6 to both sides, square root, and subtract the 5. And then these would be the inverse equations. The last way that I might test you on inverses is I might give you a table or a graph and ask you, are those two equations inverses of each other? So let's say, for example, I gave you a graph that looked like this. And then I gave you an inverse graph. Like that. And I say, are these the inverses of each other? And all I'm looking for you to recognize is the two different rules that we talked about for deciding if graphs and tables are inverses. So in order for tables, or for graphs to be inverses of each other, they have to flip over the line y equals x. Meaning if I take that brown graph and fold it over that dotted line I just drew in, it should match up perfectly with its inverse. If I were to do that here, I can tell that these are not going to line up perfectly, therefore they're not inverses. In a table, what we said is whatever is in your x column on your original ends up being the y column on your new graph. So if it was like -2, -1, 0, 1, and 2, and then let's say 9, 4, 1, 4, 9, that would mean that in our inverse table, what I should see is the exact same numbers but in the opposite columns. So these are not inverses because they don't line up. These would be inverses because the numbers are exactly flipped between the x and the y column. Last target is describing key features. So I'm going to give you some sort of equation. It could be linear, it could be exponential, it could be quadratic, something that you're familiar with, and I'm going to ask you to graph them. So I have two different equations here. I'm going to graph the first one in orange, the second one I'll do in green. So this I see, hey, it's a linear equation. That means it has a y-intercept and it has a slope. So it starts at 3, has a slope of 5, So that's going to look something like that. The other one I see has an x squared. That tells me it's a quadratic equation. It starts down here at -4. And don't worry, you'll have real graph paper. I just don't have any right now. Then I might ask you to find different important features of your graphs. So for the first one, it's just a linear equation. So I might ask you to find like the x-intercept and the y-intercept. So the y-intercept is a lot easier to find because it's part of your equation. So I know that the y-intercept is at 3. However, if you just write 3 on the line, you are wrong. That is a number. I want to know the intercept, which is a coordinate point. You must write it as a coordinate point. X-intercept is a little bit more challenging to find because what I'm asking you for is where does it cross over the x-axis, meaning when is y 0? So you might actually have to do some math for that one. So to find my x-intercept, I'm going to plug in 0 for y and solve for x. So I subtract the 3 from both sides and I'm going to divide by 5. So what this is telling me is that my x-intercept is at -3/5, comma, 0. Moving on to our parabola, I might do the same thing. I might ask you about x-intercepts and y-intercepts. So for example, the y-intercept here, I'm asking when x is 0, and if you were to figure that out, it would be at 0, -4. Again, it needs to be a coordinate point. Just writing -4 is not correct. Since it's a parabola, I know that it probably has 2 x-intercepts. Those are right here. Again, you can plug in 0 for y and solve. So I'm going to pretend that I don't see those for the moment. And I'm going to plug in 0 for y and solve. So I would add the 4 to both sides and take the square root. Keep in mind that when we take a square root, technically we're supposed to have a plus and a minus in front of that. So the square root of 4 is 2. So plus or minus 2 are my x-intercepts. So what that's telling me is my 2 x-intercepts are at 2, 0, right there, and -2, 0, right there. Might also ask you to find me the vertex. In this particular case, the vertex is right here, which also happens to be our y-intercept. And your axis of symmetry is always going to come from your vertex. Whatever the x-coordinate of it is your axis of symmetry or your line of symmetry. So in this case, x equals 0. So those would be key features. Hopefully this helps you. So just to kind of give you an idea, when I was working on my version of the toolkit, that's just kind of how I laid everything out. I used very similar problem types on here, and just a few different little reminders for you.